600 meters beneath the surface of the ocean, the world behaves according to rules that most people never have reason to consider. Sunlight has vanished long before this depth. What little warmth the sun delivers to the sea has been left behind in the first 200 meters, and everything below that exists in a permanent cold that hovers just a few degrees above freezing. The pressure at 600 meters is roughly 60 times what a person feels standing on a beach, enough to collapse an unreinforced steel drum, and enough to make the simple act of sending a machine down and bringing it back a serious engineering problem. It is into this environment that a growing number of companies, governments, and research institutions have begun to look, not out of curiosity alone, but because the seafloor at these depths and far deeper contains metals that the modern economy has come to depend on. And when one of those surveys registers a signal that suggests gold, or the far more common accompaniment of copper, zinc, and rare earths, what follows is almost nothing like the story the phrase "gold found beneath the sea" tends to summon. The image most people carry is inherited from a much older tradition. It is the image of the sunken galleon, the Spanish treasure fleet scattered across a shallow reef, chests of coins spilling across the sand where a diver can reach down and lift them into the light. That version of underwater gold is real, and it has produced some of the most famous salvage operations in history. But it belongs to a different category entirely. Shipwreck gold is refined, minted, and human-made, resting in water shallow enough that a diver with mixed gas equipment can sometimes work it directly. What lies 600 meters down is something else. It is not treasure in the sense of coins and bullion. It is geology. It is gold, still bound inside rock, dispersed through mineral deposits at concentrations measured in grams per ton. And reaching it requires not a diver with a lift bag, but an industrial apparatus closer in scale to offshore oil production than to anything resembling salvage. To understand what actually happens, it helps to understand where seafloor gold comes from in the first place, because its origin explains almost everything about why extracting it is so difficult. Along certain boundaries of the Earth's crust, where tectonic plates pull apart or grind against one another, seawater seeps down through cracks in the ocean floor until it reaches rock heated by the magma below. That water, now superheated to temperatures that would be impossible at the surface, but which remain liquid under crushing pressure, dissolves metals out of the surrounding crust and rises back up, carrying copper, zinc, iron, gold, and silver in solution when this scalding, mineral-laden water erupts back into the near-freezing ocean. The sudden change in temperature forces the dissolved metals to precipitate out almost instantly, building the dark chimneys known as hydrothermal vents, and, over thousands of years, laying down what geologists call seafloor massive sulfides. These deposits are the closest thing the deep ocean has to a concentrated ore body, and some of them do contain gold at grades that would be considered rich on land. There is a second kind of deposit that draws even more attention, though it usually lies far deeper than 600 meters. Across vast plains of the abyssal seafloor, particularly in a region of the Pacific between Hawaii and Mexico, the bottom is scattered with polymetallic nodules, lumps roughly the size of a potato that have grown over millions of years as metals slowly accreted around a fragment of shell or bone. These nodules are rich in manganese, nickel, cobalt, and copper, the very metals that battery manufacturing has made suddenly precious. They rarely carry significant gold, but they are the center of the commercial and legal storm around deep-sea mining. And any honest account of what happens when valuable metal is found beneath the sea has to reckon with them. The distinction matters because the public conversation tends to collapse all of these into a single fantasy of underwater riches, when in reality the geology, the depth, the economics, and the law differ enormously from one deposit type to the next. So consider what genuinely occurs from the moment a promising signal appears. It almost never begins with anyone seeing gold. It begins with data. A survey vessel tows sensors across the seafloor, mapping the terrain with multibeam sonar that builds a picture of the bottom from the timing of sound waves, and measuring subtle variations in the magnetic and electrical properties of the rock below. An area that might hold massive sulfides shows itself not as a glint of metal, but as an anomaly in these readings. A patch where the rock conducts electricity differently than its surroundings because of the metallic minerals within it. Only after the anomaly is identified does the slower work begin. Remotely operated vehicles, tethered to the ship by cables that carry power and data, descend through the black water to photograph the site and collect small samples with mechanical arms. Those samples are brought to the surface, cut open, and analyzed in a laboratory. And it is here, often weeks after the first hint of something valuable, that anyone can say with confidence whether gold is present and in what quantity. Even a positive result is only the beginning of a very long and uncertain road, because a single rich sample tells you almost nothing about whether a deposit can be mined at a profit. The central question in mining, on land or beneath the sea, is not whether a metal is present, but whether it is present in enough volume, at high enough grade, and in a form accessible enough to justify the staggering cost of extraction. A promising sample might come from an unusually rich pocket surrounded by barren rock. Establishing the true size and consistency of a deposit requires systematic sampling across the whole area. And at 600 meters below the surface, every one of those samples is expensive to collect. Companies routinely spend years and tens of millions of dollars on exploration before they can even estimate what a site contains, and many deposits that look extraordinary in a single core turn out, on fuller investigation, to be too small, too scattered, or too low grade to be worth pursuing. If a deposit does prove large and rich enough to consider seriously, the engineering challenge becomes the dominant reality. And it is here that the romance of the idea dissolves entirely into the hard physics of the deep ocean. Extracting metal from the seafloor is not a matter of scooping up rock. The most developed plans involve a set of machines that crawl along the bottom, breaking and gathering the mineralized material, which is then pumped as a slurry of crushed rock and seawater up a riser pipe, hundreds or thousands of meters long, to a vessel waiting at the surface. Everything about this is difficult. The collector machines can weigh hundreds of tons and must operate in complete darkness, in near-freezing water, under pressure that leaves no room for the small failures that would be trivial on land. The riser system, the long column that carries the slurry upward, has to survive currents, storms, and the constant abrasion of rock moving through it at high speed. On the surface, the ore has to be dewatered, and the leftover water, now full of fine sediment and dissolved metals, has to go somewhere. A single point of failure anywhere in this chain can halt the entire operation, and repairs at depth are neither quick nor cheap. The most instructive lesson in all of this comes from a project that was supposed to prove the whole concept could work. A company called Nautilus Minerals spent much of the early 21st century developing a site off the coast of Papua New Guinea, known as Solwara 1, a seafloor massive sulfide deposit rich in copper and gold lying in waters over a kilometer deep. Nautilus built the seafloor mining machines, secured a mining license, and became for a time the most advanced deep-sea mining venture in the world. Yet the project never extracted commercial quantities of anything. The costs ran far beyond projections. Financing proved harder to secure than expected. Disputes with the government of Papua New Guinea multiplied, and local communities along the coast raised sustained objections about what the mining would do to waters they depended on. By the end of the decade, the company had effectively collapsed, leaving behind expensive machinery, a heavily indebted government partner, and a cautionary example that the industry still studies. The story of Solwara 1 is a more accurate answer to what happens when gold is found beneath the sea than any tale of sudden riches. because it shows how a genuinely valuable deposit in the hands of a capable and well-funded company can still fail to become a mine. Beyond the engineering and the economics lies a set of legal and environmental questions that have grown into one of the defining resource controversies of the era. Much of the deep ocean lies beyond the territorial waters of any nation, in what international law calls the area, a portion of the seabed designated as the common heritage of humankind and governed by a body called the International Seabed Authority. No commercial extraction in international waters can proceed without its authorization. And for years, that authority has been working, slowly and contentiously, to finalize the rules that would allow mining to begin. The delay is not merely bureaucratic. It reflects a genuine and unresolved scientific uncertainty about what deep-sea mining would do to ecosystems that remain among the least understood on the planet. When deposits lie within a country's own waters, as many of the gold-bearing sulfides do, national governments hold the authority, but they face the same scientific unknowns and often intense pressure from the communities whose waters and livelihoods are at stake. The environmental stakes are not abstract, and they deserve to be stated plainly rather than dramatized. The seafloor at these depths is not the barren desert it was once assumed to be. Hydrothermal vents in particular host some of the strangest and most specialized communities of life on Earth. Organisms that survive not on sunlight but on chemical energy drawn from the vent fluids, forming ecosystems that exist nowhere else. Mining a massive sulfide deposit means destroying the very structures these communities depend on. Even setting the vents aside, the act of stirring up the seafloor creates plumes of fine sediment that can drift for great distances and settle over life far from the mining site, and the deep ocean recovers from disturbance with extraordinary slowness. Studies of areas disturbed decades ago have found that the marks and the ecological damage remain plainly visible, because life at these depths grows and reproduces on timescales measured in decades and centuries rather than seasons. This is the crux of the scientific objection. Not that mining the deep sea is impossible, but that we may cause irreversible harm to systems we have barely begun to understand, in pursuit of metals whose necessity is itself contested. That contest over necessity is worth pausing on, because it is where the entire question ultimately turns. The strongest argument for deep-sea mining is that the transition away from fossil fuels demands enormous quantities of copper, nickel, cobalt, and other metals, and that mining them on land carries its own severe environmental and human costs, from deforestation to the labor conditions in some terrestrial mines. Seen this way, the seafloor represents an alternative source that might, at least in theory, spread the burden of extraction differently. The counter-argument is that improvements in recycling, advances in battery chemistries that rely on more abundant materials, and more efficient use of the metals we already have could reduce demand enough to make opening a new and poorly understood frontier unnecessary. Both positions are held by serious people, and neither can be dismissed. Gold specifically occupies an odd place in this debate, because unlike battery metals, it is not essential to the energy transition. It is valuable chiefly as a store of wealth and for certain industrial and electronic uses, which means the case for disturbing a deep-sea ecosystem to obtain it is considerably harder to make than the case for the metals that genuinely have no easy substitute. So the honest answer to what actually happens when gold is found 600 meters below sea level is that in almost every case, very little happens quickly, and often nothing happens at all. A signal appears in a data set. Samples are collected at great expense and analyzed with care. Engineers assess whether the deposit could ever be reached, and financiers assess whether it could ever pay for itself, and lawyers assess who has the right to touch it, and scientists warn of what might be lost. Most promising discoveries dissolve somewhere along that chain, defeated not by any single obstacle but by the accumulated weight of all of them. The deposits that survive every test still face years of permitting and public scrutiny before a single machine touches the bottom. The deep ocean does not surrender its metals the way the shallows once surrendered sunken coins, and the distance between finding gold beneath the sea and profiting from it is measured not in the depth of the water, but in the length of the road that discovery only begins. What remains, in the end, is a more sober and in some ways more remarkable picture than the fantasy it replaces. The fact that we can map the seafloor in fine detail, send machines to work in an environment more hostile than the surface of some planets, and identify the precise mineral composition of rock a kilometer beneath a ship is itself an extraordinary achievement of engineering and science. That we hesitate to use that capability, that the finding of a valuable deposit sets off not a rush, but a long and difficult argument about cost, consequence, and responsibility, may be the most telling detail of all. The deep ocean is one of the last places on Earth where the question of whether we should do a thing has not yet been overtaken by the fact that we already have. When gold is found 600 meters down, the most important thing that happens is that we are forced, at least for a while, to decide what it is actually worth.